Let's record. Not here, I got it. Hey, where's the finger? Where's the finger?
Any questions? Anything about the open rows, inverse, inverse? Okay, let me go back to the problem that I wrote. A is a singular matrix. Then the question is whether follows that what about the denominator? The second question, does it follow that the root inverse denominator assuming that it exists? Because the root inverse does not exist. Okay, now the reason why we are asking this question is these two notions extend the notion of usual inverse here. And for the usual inverse, we know that if you have an invertible matrix, then the usual inverse is normal. So this is just an analogous question. Any answers for this? We have time to examine. Okay. See, this is the answer, and that's all part of literature. If A is a singular matrix, then A hash may not exist. The group inverse may not exist. Now consider the case when the group inverse exists. That corresponds to what are called as singular irreducible matrices. Okay, so let me address this question. A hash may not exist in general. It exists in this case when A hash exists when I'll simply take V as we have this representation. A equal to x1 minus V, V non-negative. X is the fitting radius of one. So when V is 0, I hope it's clear. The general answer for this question as to whether the A hash is non-negative is no, because A hash may not be exist. A hash exists when V is irreducible. That is when A is a singular irreducible matrix. So this is the same as saying A is a singular irreducible matrix. So it's an N matrix because this is equal to the radius of V. The further assumption is the irreducibility. Irreducibility here means that if you draw the graph corresponding to say that it will be strongly connected. Between any two vertices, there is a directed path. Singular irreducible matrix. In this case, again, A hash is not non-negative. See, this guarantees the existence of the group inverse. Even then, in this situation, A hash is not normal, but it satisfies something that's more with a less requirement, so something that's weaker than requirement. A hash to be normal. This is the problem. So there is a theorem for A hash. I'll come back to later. This theorem tells you that if A is a singular irreducible matrix, we have the following conditions. First one is that, see, I'm always assuming that A is n cross n. The first thing is the rank is n. That is, the null space is one dimension. Second statement is that every principal submatrix, of the matrix C is an invertible matrix. Every principal submatrix of A is an invertible matrix. It is an invertible matrix. Principal submatrix. Every principal submatrix except A. So I'll say every proper principal submatrix. Every single the proper principal submatrix of B is an invertible n matrix. So you have almost what you have for n matrices, but there is a gap because it's a singular matrix. Condition C tells you that E is almost monotone. A is almost monotone. What is this thing? The monotonicity is this. Monotone means X non-negative implies X non. Almost monotonicity is X non-negative implies X equals C. That is almost monotonicity. X non-negative implies X equals C. So this is one kind of a monotonicity. There is another final condition which tells you that what we have for a singular reducible matrix. It has to exist, and it has its non-negative on real. This is the term. It has a non-negative on real. Yes. Yes. That's called almost monotonous. That is correct. Yeah.
So the Laplacian matrix of a connected graph is an example.
Absolutely. The Laplacian matrix of a connected graph is an example of a singular irreducible. You take a connected matrix, draw the Laplacian, use the Laplacian. That's a typical example of this hypothesis, and so it satisfies these. Yes. So see what is going on here. You don't have monotonicity. X non-negative implies X non-negative. Remember, we were discussing this. This is called monotone. And Richard said this condition is called a monotone matrix. See, the A is square. The A is square. And this condition, monotonicity, I'm calling it monotonicity. You can only A inverse exists. And A inverse non-negative without any Z structure. Let's understand, there are no Z structure. Without Z structure. A square monotone matrix, a square matrix is monotone, you can only use inverted, and the inverse is non-negative. No Z structure. They is rectangular. This definition still makes sense. They is rectangular, this definition still makes sense. Don't have any problems. Ax is in some space, X is in some space, doesn't matter. But it makes sense. In this case, monotonicity is characterized by the fact that A has a non-negative left inverse. A has a non-negative left inverse. So we are talking about rectangular matrix. R. I'm talking about order. A has a non-negative left inverse. That is meaning what? There is a matrix Y, which is R n cross n, such that Y is non-negative and Y is equal to. These are the first one is easy to prove. The second one is not easy. Second part, there's a rectangular matrix that's monotone has a non-negative left inverse. You have to use Parkha's lemma. You can encounter Parkha's lemma. So you need to use either Parkha's lemma or the principle of duality. There is no duality gap between a primary linear programming problem and a two linear program. You have to use either of these two problems, which in turn are equivalent. So for the second one, you need to use Parkha's lemma. So I'm going to leave this for you, but try to prove using Parkha's lemma. No Z structure. This is true for any matrix A. No Z structure here. So it is the same implication. A is non-negative and then X non. Same implication. So there is something that's going on. So one can ask as to what is the condition that corresponds to the Moore-Penrose inverse being non-negative? What is the monotonicity thing? What is the monotonicity condition that corresponds to the Moore-Penrose inverse being non-negative? Okay. So if this is square case invertible, then we are in the generalized inverse case. Any left inverse satisfies three equations of the Moore-Penrose. Is that the clear thing? Any left inverse. See, Ya equals I. Then look at the four equations for the Penrose. A. Ya is I, so this is A. Ya is I, so this is Y. Look at the final equation. The fourth equation, Y star, in this case, it's a transpose. That is identity transpose, that is identity, that is. So a left inverse satisfies three equations. And so a left inverse is an example of what we call as 1, 2, 4 inverse. The more Penrose, the Penrose equations have this chronology. Equation 1, equation 2, equation 3, equation 4. So if you have a matrix A which has a left inverse, then the left inverse satisfies equation 1, 2, and by the way, can you see that the left inverse case corresponds to the columns of A being linearly independent? The matrix at the left inverse economic columns are linear. Can you prove at least one implication? Suppose Ya equal to identity. Can you prove from this that columns are linear independent? No, because it's abnormal. What is the point? Why? Is that A has a non-negative, A has a left inverse. Show that the columns are linearly independent. Columns are linearly independent. It's the same as saying that the homogeneous equation A is equal has zero economics. That's easy. A is equal to 0, we multiply the Y. You get Ya is equal to 0. Ya is identity. So A is equal to 0 and then X equal to 0. So this corresponds to the columns of A being linear. Right inverse will correspond to the rows being linear. So you can think of more general objects than the Moore-Penrose inverse. If you have come across these items, which are the left inverses and the right. For example, the questions are following there. What is it that we are keeping track of? See, we are keeping track of how to get a characterization for this statement in the more general framework. When you are either looking at the group inverse or the Moore-Penrose. Okay. So what is happening here is that this last condition is the following. Condition B precisely states the following. Suppose Ax is non-negative. If X belonging to the range, this is an implied. that x is non. This is what this condition says. In fact, it actually says x equals 0. It actually says x equals 0. But this is the condition that this statement be. So can you see that this is the left hand side generalization. Right hand side is A inverse equals A inverse non-negative. A hash equals A hash non-negative. A dagger is non-negative, etc. What I want is a statement that will be equivalent to these statements. The statement that's equivalent to this or this having a non-negative left inverse, this is monotonous condition. Can you see that this is extended to this situation? That is, it is asking for this is asking for x to be non-negative with just this condition. This is asking for x to be non-negative, not just with this condition. You also impose another condition. So this is weaker. This is weaker than that. And you see, you are asking for more conditions to approve the same thing, which is x non-negative. Here it is just Ax non-negative. You are saying that Ax is non-negative is not enough for to conclude x is non-negative. I want some extra condition. The condition is range state of A. And so this is a more general thing. So this is not the group inverse non-negative, but a more general form. Okay. Such things are called. This is called range monotones. Monotone on the range space. This is called range monotonicity of the range monotonicity of the matrix. Now there is a little simple exercise for you, which is suppose that a matrix A has a law that the group inverse is non-negative. Group inverse exists and it is non-negative. Show that in N1. So this is stronger. Asking for the group inverse to be non-negative is stronger than this requirement. Meaning that this condition implies this. A group inverse non-negative implies range monotones. Give an example for the converse. So these are not the same. These are not the same. Okay. And this is clearly weaker than the requirement that the group inverse is non-negative. But this is what comes out. I mean, you have to take it. I hope it's clear. So we are trying to look at situations where our results can be improved in some sense. We are trying to look at conditions that can be extended to more general variables. This condition is about a square matrix, so we are talking about the inverse. But if you go beyond that to rectangular matrices, then you know what's going on. There is no change here at all. There is no change in the definition. You simply impose that A is rectangular. You get this condition. But observe that if A is square, this reduces to this. This is the same as this because the matrix has a left inverse. Square matrix, it will have right inverse. And then these two coincide. So this Y will have to be the inverse of the matrix. So this reduces to this condition when M is N. And the matrix is not rectangular but properly square. We are looking at more general objects. This itself is a general object. This itself, we haven't realized it. This itself is a general object. This itself is a part of the four Penrose equations that we have encountered. So this already talks something about the Moore Penrose inverse. I'll come to the Moore Penrose inverse, but for the group inverse, this is the answer. Now, as was pointed out, singular irreducible M matrices are important for. They are important because of their application. Invertible M matrices are important. Variety of solutions. See, for example, there are some differential equations which need to be solved numerically. Now, when you solve the equation numerically, what you do is to replace the derivative by the condition. So you employ finite difference methods. Now, when you employ finite difference methods to solve these equations, what you will get is a system of equations, an implicit equation. Ax equals b, that needs to be solved. That is what you do is you take the interval, divide it into subintervals, and then apply the differential coefficients Those are the unknowns. You have the boundary conditions. Those will be the known objects. You also have the input, that's the right hand side. Ax equals b. So you have this information. You need to find the value of the function at the intermediate points. You have the boundary, but that's an implicit equation. So you solve a matrix equation. Now this matrix that comes out of such situations is E matrix. It turns out to be a strictly diagonally dominant Z matrix, and so it's an invertible matrix. In some examples, it turns out to be diagonally dominant, but not strictly diagonally dominant. But along with irreducibility, it will be invertible. So different situations arise when you look at this system of equations. So these are problems that come from practical evidence. See, there is an input-output economic situation. See, there is a set of industries, which depend on each other. Let us say there are 100 industries in a closed economy. So-called closed economy, they don't take help from outside. They don't take raw materials from outside. They also don't supply their outputs to outside people. So there's a closed economy, let's say industries. They all buy stuff from one another, sell stuff to one another. This whole problem can be modeled as an equation. An equation of the type I minus B x equals C. So there is a demand, there is a supply, etc. You can model this. That's the model will turn out to be an invertible matrix. So whenever you have a right hand side vector non-negative, the solution will be non. So there are any number of situations where M matrices come. See, there's a wireless network problem that can also be an M matrix problem. So there are lots of instances where this comes. The singular is the example of a Laplace M matrix that corresponds to M matrices, but it's singular things. So there's any number of applications for M matrices. The reason why no one is interested in solving such problems. So there is this case of invertible M matrices. There is then a case of singular M matrix. But singular M matrix irreducibility takes center stage because of the number of places that it appears. Singular irreducible is something like the best that is available. In the best situation, you don't have nothing. You have something lesser than that, which is very important. Okay, so that's about this problem. What about the Morgan-Rosen? When is it non? The Morgan-Rosen inverse is non-negative. It's the most trivial situation. There is a theorem that was proved by. See, this is Bergman-Clemens, by the way. Bergman is the same Bergman who appeared on videos. For you in this workshop. This is from Bergman-Clemens. This is a theorem proved by. I think this appeared in 1978. There's another theorem. And he proved about it. The following number. The Morgan-Rosen inverse is non-negative. Statement B. The only way this can happen is that A can be written as x on C is 0 0. That B is an invertible element. Most trivial circumstance is the block direct product blocks of the of diagonal blocks of each. So the only way this can happen is the trivial. That is, if you take an invertible matrix, you form a block matrix. The top left part is the invertible matrix, the rest are 0. Then the resultant matrix is an M matrix. It's a single matrix. So that's the most trivial way of constructing a singular matrix. So what this result says is that that's the only way you will get non-negative. Not only that, the final statement here is that in such a case, means that either B over or B over. In such a case, A movement was inverse. Report is inverse. So that's not different between the movement was inverse. Yeah. So it's not an investing. Yeah. It's called range bound. This is a definition. That's a definition. A is called range monotone, the A satisfied. No, this is a definition. When we say definition, we say economic.
He's saying B if and only if that makes before the condition B is equivalent to that.
Yeah.
If that makes A sharp like this and the fourth condition in the A sharp exists and A sharp is not similar.
Yeah, no, it's the same. Yeah, yeah. What is the meaning of this? What is the meaning of this? Yeah, see, I understand the question. See, what we have done here is we have replaced non-negativity of A dash by some statement. All that I want to say is that that statement, when you translate it to some kind of a monotonicity, it is precisely this. Even though, see, let's understand that on the one side you have monotonicity condition, A is non-negative, B is non-negative. On the other side, you have a statement involving the inverse or the left inverse, etc., or the group inverse or the multiple group inverse. What I am now saying is that A hash being non-negative is not true, but we have something B plus, which is that A hash is non-negative on the range of A. What is this? What is the monotonicity statement corresponding to this? The monotonicity statement corresponding to A hash being non-negative on range of A is this A fact, and that's an exercise that you can try and do. This statement is equivalent to this statement. Try and prove. So what is the meaning? The meaning is take this statement. If this holds, first show the A hash index. First show the group inverse index. For the group inverse to exist, there are some equivalent conditions. First one, A hash equals equal to A. Null space of A equals null space of A. This happens only A. Range of A equals range of A. This happens only A. Range of A and null space of A are complementary functions. So there are several equivalent conditions. Range and null space are complementary. Complementary subspaces here means that range of A plus null space of A is the whole space Rn, and that the intersection is true. Range intersection null space is true. That's the definition of complementary subspace. This is one standard thing that I find very useful to prove when you want to show that A hash is null space condition. So the exercise, the first is the second part is to look at and all this condition what GP also. Show that GP implies A hash and implies condition B. Whenever x belongs to range of A, the action of G hash on such an x is non-negative, the moment x is not. The moment x is also non. That is non-negativity on range. So condition D, I am rewriting condition D. The meaning of this is that A hash x is non-negative whenever x is non-negative and x belongs to range of A. That is condition D. A hash non-negative on the range space means this. Now you can see Okay, that's what this means. Now you can see that this is the condition that replaces. I'm just trying to build in some equivalences here. See, what is the meaning of A inverse non-negative? A inverse non-negative, if not non-negative, X non-negative implies A inverse X. A matrix is non-negative if it leaves the cone R inverse. X belongs to R inverse, A inverse R inverse is non-negative. A inverse R inverse is an R inverse. That's non-negativity of the inverse. Now you can relate this as a more general framework than this. X non-negative does not imply A hash X non-negative. But if it also belongs to the range of A, then it is. So, well, not too much in the am I? This is not the method. Yeah. Yeah, now this is a stronger condition. A hash being non-negative is a stronger condition than range monotones. That is, we can show that whenever A hash is not A is range monotone. That is this condition. This is that, right? So I'm asking you to show that to be equal. So if A hash is non-negative, you can come back and see. If A hash is non-negative, this condition is not required. If A hash is non-negative, X is non-negative, A hash X will be non-negative because of this condition. That's why I said A hash non-negative is a stronger condition that will imply range monotonicity, which is this. Range monotonicity is equivalent to the condition. That's what I'm asking you. So that is trivial, but this is weaker. This is weaker than the requirement that the group inverse is not, which never happens. Group inverse non-negative never happens. It is indeed. But what you have is this. What you have is this. This is called group monotonicity. It's called group monotonicity, range monotonicity. There are several names for that. So that's the situation for the group inverse. More controls inverse, nothing. The most trivial thing that is true is the only possibility if you ask the more controls inverse of a singular lemma matrix to be known. Questions?
Exercise use and matrix or inverse.
GP condition, any matrix. No Z. No Z. No Z condition. This group monotonicity, range monotonicity implies for one thing the group inverse exists, and for another the group inverse is non-negative on the range space. That is for any matrix. Okay. That is for any matrix. If A is a singular irreducible n matrix, then that happens. This condition holds for such a matrix. Okay, this equivalent statement holds for any matrix. Just as how the equivalent statement that A is monotone economic A inverse X non-negative holds for any matrix. This equivalence holds for any matrix. That one of those two happens for a singular irreducible n matrix is formed. Of this way. Okay, so this is all you can hope for. This is the best that you can take. Now this is for objects that are to the right of the spectrum. Either the spectrum radius or to the right of the spectrum. You are writing A as SI minus B, where B is non-negative, and S is either equal to the spectrum radius or to the right of the spectrum radius. What happens when you go to the left? What happens when the spectrum radius condition? What happens to the matrix when the spectrum radius condition goes to the left? What is the meaning of going to the left? So let's try and understand that situation. There is a whole theory that's happening there. Just like how on the right you have this n matrix, singular n matrix, invertible n matrix, so then you have invertible Z matrices. Okay, but that's not as well understood as the matrix case. So I'll try and discuss that in the rest of the list. But I just want to point to another notion called the H matrix. The notion of what's called as the H matrix. This is closely related to the Z matrix notion. The M matrix goes with impossible. H matrix we don't know who's doing that. What is a H matrix? You be given a matrix A, or n cross n.
Z is the Z matrix also we don't know what the Z means.
This one?
Z.
No, Z that Z comes from some German word. What's it? It's not an element. Zahlen theory is something I don't know, but it's concept, it's a notion from German. This H is not there. Okay, given matrix A, what you do is you write down what is called as a comparison matrix. The comparison matrix of A, we call it M sub A, is given by, look at M sub A, I want to simply I take M. This is defined to be absolute A is always AI. This absolute AI is equal to J, and it's minus absolute AI J. The minus not equal to the definition of the comparison. So the diagonal entries are the magnitudes of the diagonal entries of the matrix A. The off-diagonal entries are the negative of the magnitudes of diagonal entry for A. So by definition, this NK is always a zero of diagonal entry is non-positive. So you can ask the question as to whether this is an invertible index or just a singular element. If NK is an M matrix, then as it is, okay, no invertibility, imposition, then A is called an H matrix. Is called an H matrix. Now there are situations when this HA belongs to classes. There are three classes. One is so we call A an H matrix. We call A as an H matrix. If MA is the comparison matrix to the matrix. We say that A belongs to this side. If MA is an invertible matrix. There are three situations. See, one looks at what is called as the EP modular class of the matrix A. One looks at what is called the EP modular class given matrix A. What is the EP modular class? It is all those matrices whose component-wise magnitudes are the same as the component-wise entries of A. They are called EP modular. Component-wise EP modular with mod A. They are called, that is called the modular things. That is, you look at the matrix, look at matrix 1 1 1 1, 1 minus 1 minus 1 1, they belong to the same EP modular class. The moduli are the same. So these are EP modular matrices. Now, According to the Leaky model matrix, you can split H matrix into three categories. One is HL, one is HL and NA is invertible. Another one is HS is H singular. That is when NA is not invertible. There is a situation where it is called HT, HM is mixed. M is mixed. If MA is an invertible M matrix, then the matrix A is invertible, and everything in the equimodal class is invertible. So this is a very good situation. The intermediate situations are divided into mixes or HL, either the singular class or the mixed. We will be interested in this. So let's not worry too much about here. If MA is invertible, then A is invertible. That can be shown. In fact, we have the following here. This is due to orthodoxy. This is a very old theorem. It states that if A belongs to the design, we then have the form. A is invertible. Then A is an invertible M matrix. That's a situation when A belongs to the design. Right? A is an H matrix. Further, A belongs to the class H. So this comparison matrix is an invertible M matrix. Then this is the relationship between the entries of A inverse and the entries of MA inverse. What is the meaning of the modulus of A inverse? Modulus of A inverse is the matrix. It is obtained from A inverse by replacing the entries by the inverse.
Inverse is
So this
absolute value. By replacing by
absolute value. So this is the absolute value of A inverse. Absolute of the matrix A. The matrix we have absolute values of A inverse. So this is an entry wise. So this is a matrix on the left. The entry wise comparison. This is MA. This is something that's used in a number of applications. Numerical analysis, H matrices keep coming again and again, invertible H matrices. So this is the result which is useful in. See, this is an upper bound lower bound. This means the entry of A inverse go with the negative entries here and the positive. So the upper bound lower bound penalty. So this is also so there are some refinements. I just want to explain I'm not proving but this. It's not difficult to prove. You want this is the basic steps. You look at the product of the matrix. Let's say product EM. Product EM. Product EM take up. So that is better than equal. Compare the matrix corresponding to E into the one result that we will need. You also have another simple thing, you can even guess that this is typically product EM. That is not important, product E through E. Left hand side is the matrix, right hand side is optional. Then reverse. You need to multiply this matrix with this matrix and verify this. This is just the random equality. Use these two to conclude this solution. We need to first show the inverse elements. And then this. Oh, so this is one relationship with the new class, the matrix of the invertible H matrices. They are related to the comparison matrix. Okay, so what I want to now do is to go to the left here and then try to look at some random results. Random, not really random, I'm interested in those. I can give a kind of an exposure. What one does is to now look at A equal to SI minus B again. B is non-negative. So you have this. To ask this question, let's now look at the notation. Look at row n minus 1 of n. What is this? This is the definition, effective radius. This is the maximum spectral radius of minus 1 of minus 1. Principles of mathematics. I'll use this notation. Row n minus 1b. So given a matrix B, non-negative. You look at all principal submatrices of order n minus. All principal submatrices of order n. They are all non-negative. You know that the spectral radius is an eigenvalue. Or compute all those spectral radius and then take the maximum of all those. All that as a word. You now ask S. Yes, we had S greater than or equal to 30 degrees of P. Put this condition for one thing so that you don't have n matrices. The right is n matrices, and then this is the first step. Make that to be strictly greater than rho n minus 1. So look at this figure. Look at this. So it's a Z matrix. Anything that is greater than this Z matrix is a Z matrix. For the Z matrix, we had been dealing with the right answer. F greater than or equal to 30 degrees of P. We now move to the left. When we move to the left, we take step by step. We move to the left of 30 degrees of P, but we keep greater than the 30 radius of the n minus 1 order. So one thing at a time. Make this assumption, then this matrix is called an n matrix. Such a matrix is called an n matrix. Called an n matrix. Now what n is?
Will it not be?
See, this object n matrix that we encountered in the BOB structure, that's more general. See, that n matrix is a matrix, each of those principal minus is negative. That n matrix is different from equilibrium.
This won't be an M matrix.
This will not be n matrix.
For me, for sure. Like this.
No, the only thing, only m matrix is equal to 50 or the right. So this can never be n.
So we assume this.
Yeah.
Just the row n minus 1 of B.
Yeah.
We
So we
also
impose this
assume
condition. Whenever, so I have a representation here. B is non-negative. The number S satisfies this condition. I call that an n matrix. Now this is not new. This is old stuff for 4-5 decades or even more. So, but this has been investigated quite a bit. Investigated quite a bit. There's a concept. See, as I told you, there is a linear complementarity concept also related to this n matrix. But people have studied this for properties that are similar to limits. What is one property that is similar to limits? Before that, I take character. See, if you want an example, I can give you one before I move on. But it's not easy to give examples. No, unlike the M matrix case, you can easily give examples. But I'll try and give you one. Because I come prepared to this. leave it for the verify, it will take time to verify this. And just remembering the procedure to construct on that I'm doing this. It's better for you to check this. Don't waste my time first for that. This is an example of an end matrix. There is a procedure to construct an end matrix from an end matrix. So this part is an end matrix. This one is an end matrix. Just remember that procedure and see this is an M matrix because it's a Z matrix. Diagonal entry is positive, determinant positive. So this is an invertible M matrix. From this you can construct an M matrix. Okay. So that's a characterization. A is an M matrix.
So then the remaining entries are constructed from.
Remaining entries are constructed by using a procedure. See, okay. You want me to give the details? Look at this way. That is one. GA constant. This paper talking about beginning of the see, the thing is that this is not very much less intuitive than the impact systems. And so this is the harder thing. And there are some nice properties which I am. A is an M matrix. If and only A is a Z matrix. Second condition. Determinant of A is negative. Third condition. All proper principal matrix. Okay. Are convert all proper principal submatrix. Okay. Are invertible elements. So this is kind of see you can't get rid of invertible elements. They are there somewhere. So this is a necessary information. It's a Z matrix, determinant negative. All proper principal minors are invertible elements. Proper principal submatrix clearly. Submatrix of order 1, submatrix of order 2, submatrix of order up to n minus 2. Principal submatrices. So they are all invertible elements. This is n. Okay. So then we ask the question. The inverse characterization. Then this result. Note that determinant A negative, so A is inverted. An N matrix by definition is, you can see follows from this also. An N matrix by definition is inverted. See, if something is in the null space of A, something is in the null space of A, that will correspond to that's an eigenvector correspond to the vector matrix. But the moment S is less than this, that cannot. Okay, and so A is equal to 0 will imply X equal to 0 because of this. Because such a vector X in the null space will be an Peron vector, will be a vector identified with the Peron domain, eigenvalue. Now, this number, since it should be less than that Peron value, it can't be non-zero, otherwise it will be confirmation. This has to be greater than or equal to. So, any N matrix by definition is invertible. If it's not clear, this characterization is telling you the zero. So we have the form. A is an N matrix. Even only A inverse exists, and A inverse has the property that all entries of the inverse are negative. All entries of the inverse are negative. Okay, so some such thing. There's a partial order thing. A inverse non-negative is for a invertible F matrix. Group inverse being non-negative on the range space for singular. For an M matrix, this is the characterization. A inverse has all its entries negative.
Any, like anything that we can right away see that it has to be negative. Like that doesn't seem to be obvious or
That's all. And that is why I don't have any issue with this. What it says is that this matrix is invertible, inverse has a property that means entries.
so from the examples also it's not really clear.
Not clear. Not clear. So this is one category of matrices. So then there's a whole lot of theory that goes behind this. What are the number of negative eigenvalues? There are questions like A is less or equal to B. A, B are n matrices. Then does it imply that A inverse is greater than or equal to B inverse? This is true. This is true for M matrices also. This kind of question is there for invertible M matrices. So one asks the question for N matrices. Okay, now from this one can go like how one did for the invertible element to the singular element. You allow for the has to take the value equal, not greater. That's like how you do for the singular. So B in this situation, look at the closure, the metric closure of the subset of the elements. So let me just write the same notation. I'm now looking at S to satisfy because of course 50 less than 20 is of B. This time it is all of B greater than or equal to. So equality is allowed. Rho n minus 1 of B. Rho n minus 1 of B is the maximum radii of the principles of matrix of all the elements of the matrix B. You allow for equality. We call this as N naught matrices. From N you go to N naught. Just like how you go from invertible M to singular M. By the way, singular M is sometimes called MC. I'm including one more nomenclature that is already clumsy nomenclature. In NCT theory, there are so many classes. R naught, Q naught, P naught, M naught, N naught. So many. So this is N naught matrix. Now, a procedure, see, for one thing, N is contained in N. Any N matrix is N naught. In the case of N naught, it must be greater than or equal to. For N, it is strictly greater. So N is contained in N naught. It's not a thing. What you can also show is that anything in N naught is the limit of elements from N. So it's a closure of N. But it's not easy to construct N naught matrix. It's like how we do it. So that question remains. So you can think of these questions. How to construct them. So from N is what I from invertible elements. This part is an invertible element. There is a process. So how do we construct this? So this question is next.
It's a topological closure we are saying.
Yeah.
With the limits of
Limits, yeah. Anything in N naught is a limit of sequence. Simply because of this thing. What do I have? Yeah, by the way, what is this kind of a thing for an N naught matrix? It's not difficult to guess what that will be. A is element of N naught, if and only the following conditions are satisfied. First, A is a B matrix. Condition B, determinant A is negative. You had set less than or equal to 0, you are wrong. Condition C changes. Condition C there is all proper principles are matrices. All proper principles of matrices of A are M matrices. Some of them very simple. The commitment here is that each of them is invertible M matrix. There is no such commitment. Some of them may be singular. So this is just M matrix. That is a minor difference in the characterization. Determinant is negative, so it's again invertible, not still invertible. That's not a problem. It's because of this condition. So that should not be surprising. You are not allowed to go to the speckle radius or to the right of it. That's not allowed here also. So determinant is negative this time. It's invertible this time. You can in fact show determinant is negative. The difference is in the third condition. Now it's not so easy to construct N naught. So you can think of so there is a procedure in this way. How to construct an N naught, how to construct an N matrix from invertible M matrix. We have anything left up here. Properly N naught. See, it's a procedure gives an element of N naught because N is contained in N naught. But I want an N naught which is not N. I want an N naught matrix which is not N. How do I construct from an invertible N matrix? So this is N naught. What is the characterization for N naught for the non-negative P, non-positive P?
Yes, sir.
A is N naught. Economy. Suppose it is inverted. Inverse and inverse can have some zero. So this is a mild relaxation. From this condition, which is all entries on the strictly with them. Now there is an investigation into what are the other possible properties, eigenvalue properties, this kind of a inverse monotonicity properties, so they are all good. What I have been looking at of late is this. What is called an F-naught matrix?
Sir, any example? Not, it's not.
I don't have. I can give it to you. This is an F-naught matrix. See, the principal submatrices of order 1 are 0, so they are still M matrices. This is Z matrix. Determinant is negative. 2 by 2 is nothing, but 3 by 3 itself is difficult. So this is a real question, not how to construct. How to construct a proper N naught matrix which is not an N matrix. Maybe from an N matrix. Like how we did. The question remains. I'm looking at what is F naught matrices. Okay. That's what I am trying to look at. But I have never come across an F matrix. See, there is some confusion about giving names. This F is due to a person by name Fan. Suppose the pronoun has form, key form. That's the way you are supposed to pronounce. That's for us as Kai. So Kai, this is named after him. See, this Ifan is he's no more Chinese mathematician, but he is someone like Ando. He is he's very versatile in language. He has written many papers. He has written lots of papers. See, significant, impactful papers. There are papers which he has written from which they refer to it as the Kefan inequality, Kefan fixed point theorems. So he has done the versatile mathematics. He has done things in analysis, topology, algebra, like Ando writes, Ando studies something, writes, reduces the paper and does the like a benchmark, a basic paper in that area. So this man said, so this F comes from Bifan, F one side, not the N. So there is an F naught matrix. I don't know what is it. There is a confusion in the literature about why this is called F naught. So there is no F. I have searched the literature. There is no F. What is F? What is F is already N. So there is the property F. Someone refers to a class of matrices, but that F looks like N. So there is no F in class. So I look at F naught. So what is an F naught? The F naught matrix is a Z matrix. What is the definition? Give the definition. It's a bit complicated. It's a Z matrix. First condition. Second condition. All principal submatrices are forward. There is not equal to n minus 2. There is not equal to n minus 2. These are n matrices, not necessarily inverted. All principal submatrices of order less than or equal to n minus 2. So n minus 2 is the barrier. You don't even go to n minus 1. N matrix corresponds to n minus 1. These are M matrices, not necessarily inverted. That's not important. Condition 3. It has at least one principal submatrix. And at least one principal submatrix. Of order n minus 1. Not matrix. Without a substrate. See if it is different. So what you have gone is, from n minus 1 you have come to n minus 2. From n minus 1 you have come to n minus 2. From n minus 1 you have come to n minus 2. From n minus 1, what you have done is you allowed yourself this one. You have allowed yourself this one. So there is an n naught component. There is an n naught component plus this. That's this part. That corresponds to order n minus 1. For order n minus 2, you retain what is there. You want the principal submatrix of order less than or equal to n minus 2 to be M matrices. So you're actually looking at this equation. All proper principal submatrices of V order less than or equal to n minus 2 are M. So this is a combination of what you have here for a Z. So this is really motivating from this. Now the Z naught matrix can be singular. Okay, so that's one thing that you don't have. You don't have inverted. It can be singular. And fortunately for the Z naught matrix, there is a structure. we have this structure for example. So this is very useful. It has a principal submatrix of order n minus one. That at least one principal submatrix of order one, which is an n naught matrix. So that is this part A. A is a matrix n minus one cross n minus one. U and V are vectors, column vectors. V is a column vector, U transpose is a row. Alpha is a number. So this last thing is just a row. This is a column. This is n minus one cross n minus.
So I think, should we write A equal to or?
A equal
It's permutation similar to something.
so not. But practically we write A equal.
Yeah.
Because our properties don't change then. You do this permutation symbol. So this is F naught. For this F naught, we can ask. See, this K is an N naught matrix. So K is a Z matrix. Let's just remember. All these are Z matrices. See, these are the octagonal parts. These must be non-possible. So these are non-possible vectors. And this alpha is just a number. It is an intersection of this row and this one. So what is the determinant of such a matrix? In terms of K and someone using the show component. Using the show component. So hereafter I left it way as this. Into the show component. That is alpha minus U transpose K inverse. This is the number. This is the number. Okay. U transpose K inverse V is a generalized product. The number is the number. And so K is invertible. See, this K is an N naught matrix. So it is not zero. Any N naught matrix is invertible. So K is invertible. Alpha inverse U transpose K inverse. So complements are. What is the thing that K inverse is see the N naught matrix situation. So K inverse is not equal to U and V are also non-positive. So this object is non-positive. The transpose K inverse V is not equal to. The alpha should not be this. What happens to the inverse of it? Matrix. K is an N-naught matrix. So by addition inverse, the inverse is not. What happens to the inverse as a question? So yeah. That is alpha. Greater than 1. You know why? First, greater than 1. Why? Not from this. It's from this. All principles submatter of order less than 1 since all diagonal elements must be non-zero. They are n matrices. All principles submatter are n matrices. Diagonal must be at least 0, greater than or equal to 0. So that's one just one observation. So let A be invertible and these are the ways to get it. I'm just writing down something here. Go it. But I want to compare this with one new. Then A inverse. Right? We are interested in asking whether A inverse is not equal to 0 or something like that. But what we have is that A inverse is a D inverse. So that is one positive diagonal. Okay, so there are some sign patterns. It's not just either all non-negative, non-positive. There is sign pattern. Inverse has a Z sign pattern. So all diagonal entries are non-positive. About the diagonal entries, there is no full comment, only partial comment. At least one of them is false. At least one of them is false. We don't know about the test. No other conclusions. This is for the inverted matrix. Now we looked at the singular case. We looked at the singular case and got a problem. I wanted to compare that with this. Okay, see, so it's a benchmark. This is like a benchmark now for F naught matrices. This is invertible. What happens to the singular case? When you have invertible F matrix, you look at the singular case, singular F matrix, what happens to analogous statements? Are they true? How much are they true?
Take one. So is it like if all the diagonal entries are negative?
No, the diagonal entries, none of them are negative.
Because inverse A inverse.
For A inverse.
If suppose it's there, then I think A will become M matrix. A that means it's not. I'm saying at least one positive diagonal is required. Like expecting
for the inverse.
Yes, sir.
Yeah, for the inverse of it. Yeah. Not for A inverse. Yes. This is now a statement about A inverse. See, A has the property that it has all the diagonal entries are non-negative. Because A is an F naught matrix and you require this condition. All principal submatrices of order F naught M minus 2 are M matrix. So all diagonal entries of A are non-negative. There is no negative with them. If you look at A, so statement 2 is only about A inverse. A inverse is a Z matrix. When you say something about the Z matrix, you don't say anything about the diagonal entries. Z is only about off diagonal entries, not off. Here there is an extra condition that it has at least one diagonal entry for. So that is for the invertible. Okay, so what do we do for the singular? This is one. So this is one of my notes. This is an archive. Okay, have access to this. A is singular this time. So they're asking what happens to the more than percent plus of the group. Of A is n minus 1. So like a singular matrix. Rank of A is n minus 1, n minus 0. A hat is okay, this is again interesting because singular matrix, there's no guarantee that the group inverse exists, but here it does. Like the singular irreducible n matrix. So this is the analogy that we always look at. What is the third statement? The A is reduced. The A is reducible, then reduced. Then we have this. Improve statement 4. The A is irreducible. And n equals 3. Then again, we have to 7 or equal to 0. That one is not equal to 0. The water was inverse also. This is the limits. Here you don't have. Here you don't have. You have less than or equal to 0. That is not. So there is a difference in the behavior in the movement of inverse of that.
So A is only reducible.
Yeah. So let me start on. So you have singular irreducible economic matrix. Then A dagger is a Z matrix. Singular reducible. Singular reducible. So I want to compare this with what we have here. Singular reducible. The group inverse is non-positive, so it is trivially a Z matrix. But even if you look at the case in NS3, it is reducible. The group inverse is not necessarily non-positive, but it is always Z for n equals 3. N greater than or equal to 4, we don't know things. N greater than or equal to 4, we don't know things. Irreducible is not. N equals 3. So we have this is something.
From n equal to 4.
For n equal to 4, we have no idea. See, for the general statement for any n is only this statement. A is reducible, then the hashes does not equal to 3. All these statements are for n equals 3. For n equals 4, we don't see we have completed some examples, but they turn out to be the conclusion turns out to be the same, but they're not able to give a proof. Not able to give a proof. They are able to give a proof only in this case. N is 3. So this is fully n equals 3. This is a general statement. Group inverse 1 by x. Stop here. Next question.
Yes.
It's not difficult. This one is not difficult. Group inverse x. Full rank factorization. So I'll give you the full rank factorization for this. This is just K U transpose. K is inverted. So K U transpose. This is the F part. The G part will be its identity. K inverse. This is the full rank factorization. Okay. So we get this K. K inverse means and U transpose I have to U transpose K. Sorry, U transpose K inverse is alpha. That is because it's single. You have the single equation. This is invertible. This is 0. So alpha must be U transpose K inverse C. That's how you get this U transpose K inverse to be alpha. Then it is 0. So complement is 0. This is the full rank factorization. Show that GF is invertible. So that GF is invertible. That's the thing called Sherman-Morrison formula. Sherman-Morrison formula for finding the inverse of the rank 1 update. The A is invertible. You want to know when A plus UV transpose is invertible. That is Sherman-Morrison. So group inverse X is 0. Almost immediately. Okay, so that's some motivation. Kind of things that you are taking down. See, for example, this n matrix or n short matrix, it has not been studied in the case of the second order form, in the case of the Lorentz on R. What kind of results will you for the second order form? There can be one full line of results. And see, there is this, see, if you are looking at the semi-definite situation, see, if you are looking at operators on Sn, then the Lyapunov operator and the Stein operator, they are both zero. They are both zero operators. We can ask when they are non-positive. Meaning, when is the Lyapunov operator? When does it have the property that is invertible? And the inverse keeps the negative semi-definite form in variable. When does the inverse keep a negative semi-definite form in variable? So, this one full question. When does that happen? There is already some M matrix thing done by Fox. This can be one line of research. Okay. Thank you.
Thank you, sir. Thank you, sir.
Just 1 minute. I want to make sure that 12 people are coming for tomorrow's excursion to Murdeshwar. I think 12 people have filled the Google form. Puran Dangal, Anjan Gautam, Rajia VK, Haritha T, Sajal Gaur, Kranti Priya, Rahul Roy, Shivangi Yadav, Anjita Ashokan, Komal Kumari, Aditi Auladar, Samapti Pratihar. Anyone else interested to come? Sure. Okay, just give me the. If anyone is interested, please fill the details here. Don't fill the Google form. Okay, fill the details here. Yes. Yeah. It's 80, no, maybe 25. You're not good. Murdeshwar. You must have gone on it. You must have already seen it. She didn't come with us. will be given right. Yeah, it will be. And I don't have that. Why is the reason? Why ever it is plus name? If it is then we will right. So oh yeah, that's why I entered plus name on separate. Otherwise, it makes it as zero. Wait, now did you change the no, it was Google Sheet. Oh, no. That's true. Yeah. Huh. Huh. In the afternoon, in the road, 12:30, you are right. Yeah, from there you have to catch Manipal bus. Okay, if Manipal or Udupi. If you are catching Udupi bus, then from Udupi you will catch Manipal. So, if that is the case, if you are coming to Udupi and then catching the Manipal bus, you just in the Udupi while you catch the Manipal bus, you will have to make it not there. Yeah, yeah, right. Manipal is outside part. Okay. If you are catching Manipal bus from Mangalore, you directly come to Manipal and get down at Tiger Circle. Yeah. Yeah. Okay. Yeah, Manipal bus. Yeah. Ask me, I made it up there. Otherwise, if you catch Manipal bus from Nancy, then you have to get down at Tiger Circle. Yeah, Tiger Circle. Tiger Circle, you will get that. Yeah, or they will yeah, it is allowed. Yeah. If no, no, you can just walk or you can take a talk. Private So there I think. Oh, okay.
Slide is it.
It's the right number.
I guess. No, it is already done. Slide is it. So is it? So start recording. This is good. So that it will be. Oh, yeah. Big something. No, stop. No. One day, one day. Mike. So this is Mike. Yeah. Over. Change. Go forward. Perspective. Previous. Next one. Huh? Next. This one. Oh. Yeah. Yes. That's what I.
So we all had eaten the snack. There are more good yes. You can take if you want. No need.
I don't like it. I don't like it. Very bland.
You like it blend.
Oil and
But you like it blend.
I like other bland things.
Don't take that. There's no. We haven't eaten. This is the other no. That's very clear.
So anybody wants to be sponsored? Welcome to the last part of this lecture, which consists of two distinct topics. One is post-structural graphs. Next one is direction for further research. I have identified around 40 to 50 topics which can be tried for further research. Okay. So first, let us come to post-structural graphs. See, given that given two graphs, vertex
After question, yes, the isomorphic to this. This is called resolution problem. Can resonate the graph unity. This is considered to be one of the most difficult problems in graph. Even though graphs, how to decide whether they are isomorphic or not. We don't have any specific method or algorithm for this purpose. When spectral graph theory was started, see, if you have a graph G, you get the adjacency matrix. Suppose you relabel the graph. What will happen to the matrix? Yes, there is some permutation on the. So that is not going to change the spectrum. Therefore, early researchers believe that spectrum may completely determine the graph. May completely determine the graph. But the belief was only for 2 years. As people came out with examples to show that there are graphs which are non-isomorphic, but have the same spectrum. Such graphs are called co-spectral graphs. This is the smallest graph of order 5, which is co-spectral. Both have the same characteristic polynomial. One side is a connected graph, the other side is a disconnected graph. So this is the smallest band of co-spectral graphs. Then people ask the question, can we give two connected graphs with the first? Natural thing.
It changed.
This is the smallest pair of connected co-spectral graphs and is order 6. The smallest pair of co-spectral graphs is order 5. This is order 6. This is the smallest pair of connected graphs or co-spectral, which means any two connected graphs are order 5 or order 4, they don't have a co-spectral matrix. Okay, this is the smallest pair of connected graphs is order 6, which are co-spectral. Then people ask, can you give two co-spectral trees or two co-spectral blocks? Okay. So this is the smallest pair of co-spectral trees, now is order 8. The smallest pair of co-spectral trees is order 8. That means all trees up to order 7 have no co-spectral matrix. Okay. So this is 8. Then they will talk about blocks. And they prove that the smallest order of co-spectral blocks is 7. Now, what is the smallest order of two regular co-spectral blocks? What is the smallest order of two regular co-spectral blocks? Because regularity plays a very significant role in the study of spectrum. And they prove that the order is 10. The smallest pair of regular connected co-spectral graph is order 10. Then people ask me, what is our spectrum of two bipartite graphs? What is smallest order of connected bipartite co-spectral graphs? And they found that the answer is 16. It goes on increasing. Okay, fine. So people started working on co-spectral graphs. All the theorem is the following. Can you give me 1,000 graphs such that for every to our post vector? I wanted to give 1,000 graphs. They have 1,000 graphs. Any two of the 50 post vector. Do you think it will help? Is it possible? What you think the intuition says? I want the family of 1,000 graphs. G1, G2 up to G1000. Any two of them are the post vector. All of them are post vector to each other. Can such a thing happen? What does your intuition say? Can you have a large number of post vector graphs of the same order? Huh? What the intuition stick? Huh? I give you a large number, and I'm asking, can you give that number of graphs that the into of the mark post vector? Any two of the mark post vector. In fact, even any k, I can find a family of k graphs such that all of them are post vector. Any k, any one time or one from backward one. Even any positive integer k, I can give you a family of k graphs such that all of them are post vector to each other. The concept is very simple. You just give it to regular. I answer is you give me two regular graphs. I already said that what is the smallest part of the regular post vector graph? I think it is 10. Yes. Regular post vector graph is order 10. Minimum. You give me two post vector graphs. Okay. Regular. Okay. Two regular post vector graphs you give me. You give me k. I first take this disconnected graph where one component is h1, all the remaining are h. K minus 1 h. Take one graph, the disconnected graph I am taking. Okay. The disconnected graph I am taking. One graph is K1 or H1 or the remaining are H. Then I take two graphs H1 or the remaining are K2 and keep moving.
You're taking the union of them. Just taking the copies of them.
So here you have one H1, here you have two H1, here you have K minus 1 H. And finally, I'll make everything H. So how many graphs are there? The disconnected graphs. I will call them one notation.
G1, G2.
That is not a good notation.
G1, G2.
I'll put G1 itself, no problem. I have given you K graphs, but they are disconnected and they are post vector because H1 and H are post vector. For disconnected graph, spectrum of the disconnected graph is union of the spectrum of all the graphs. Therefore, this is post vector. Now I take the complement of this. Take complement of this. It's a connected graph now. Regular graph. Because each gets a regular. And in the morning we proved that for a regular graph, spectrum of G completely gives the spectrum of the complement. From that theorem, I see that all these graphs from the same spectrum. So when you K connected regular graphs such that any two of the bar was. So K is any big number, right? So co-spectral graphs are abundantly large. That's the first thing. Okay? The large charisma co-spectral graphs. In this direction, there's a very beautiful theorem called by Schwann. So J. Schwann is one of the experts in spectral graph. He proved a theorem. When understanding the theorem will be discussed, doesn't matter. Almost all trees are co-spectral. Almost all trees are co-spectral. What's the meaning of the statement? Almost all trees are co-spectral. What is the meaning first for the statement? That is it's not obvious, right? It's not obvious. You take all trees of order n, I denote it by the symbol tau. All trees of order n. Okay. Then I take all trees of order n, which are the co-spectral net. T has a co-spectral net. That's another tree which is non-isomorphic to this, which has the same spectrum as T. The tree has a co-spectral net associated with it. How can we interpret this number? This number. How can we interpret this number?
One.
In the language of probability,
One.
numerator is number of trees which has a co-spectral net. Denominator is number of all trees of order. Therefore, this quotient represents
Probability of.
the probability that
Yeah.
a tree has a co-spectral net. So this number represents, I call it Pn, is the probability that the tree has a co-spectral net. Okay. So what is the meaning of saying that limit n tends to infinity of this is equal to 1? First, what is the meaning of saying that as n tends to infinity, this equals tends to 1?
Almost all of these are.
If this happens, we say that almost all trees are possible. That's when it becomes, the n becomes larger and larger. The probability that it has a co-spectral rate also increases, keeps on increasing. So this is the meaning of the statement that almost all trees are co-spectral. So this is the meaning of the theorem. Even understanding the meaning of the theorem needs this much of information. So Schwann has proved that almost all trees are co-spectral. The proof runs to more than 25 pages and uses some computer search to identify some trees. Okay. I'll give an outline of the proof. For dealing with this problem, he introduced a new concept called co-spectrally rooted graphs. Okay. Post vectorly rooted graphs. You take a graph G1, fix one vertex and call it root. Arbitrarily, you fix one vertex, call it root. That is called a rooted tree. Okay. Take a second graph G2 and fix a root. Fix a root for that entity. I say that G1 and G2 are post-spectrally rooted graphs. If they are first of all post-spectral, then even after removing the tree, remove the root, it remains constant. A beautiful concept. Rooted, post-spectrally rooted graphs. Not only the graph is post-spectral, even after removing the root from both the graphs, it remains post-spectral. Okay, fine. So he introduced the concept of post-spectrally rooted graphs. Okay. So how to use this concept in the flow? Okay. The idea is, suppose you have two rooted graphs which are post-spectrally rooted. You take a third graph X and fix a root for that graph also. Okay. Take another graph, fix a root. Now put this here. Identify this root with that root. Okay. Identify this root with that root. So you get a graph like that. Root of X is identified with the root of R1. Similarly, here I will identify the root of G2 with this R1. So you can imagine the graph, X is sitting here, a G1 is attached to that. So what the adjacency matrix of this graph? X and G1 are sitting, there is only one common vertex. So adjacency graph of H is sitting as one block. Adjacency graph of G1 minus C is sitting as one block. So two blocks. Okay. Now G1 and G1 minus R1 and G1, G2 minus R2 are post vector. So this portion is post vector. So this graph looks like one block here and another block here. This block is adjacency matrix of H. This block is adjacency matrix of G1 minus the root. Just we have taken that. And what is the for the next graph? It's the same. But G1 minus K and G2 minus K are post vector. So this is common. So you have to see the matrix that these graphs are post vector. I call this H star G1 and H star G2. But star means identify the root. Star means identify the root. It's just because this and this are the same spectrum. Here the same graph sitting. Therefore, this graph is post vector. So this is the trick that is used to solve the problem. Fine. So, prospectively rooted trees is a crucial concept for the proof of the theorem. Good. What we did is, a very nice trick. We found first two trees of order 9, both are rooted trees. Order 9, such that T1 and T2 are prospectively rooted. He called them limb. T1 and T2 are called limbs. Something that you are going to face. Okay? T1 and T2 are called limbs. Then we proved that if a graph is large, if n is large, one of these two will sit there in the tree. One of these two will sit as a large tree. This T1 will be sitting here as a limb. 9 vertex tree. Okay, this 9 vertex tree will be sitting there as a limb. Then you delete this limb, put another limb. You delete that limb, put another limb. It is constructed. Okay, that's what I have just done. So in this way, you was able to prove that for a large n, almost all trees have a post-structural element, and computed the proof that almost all trees are post-structural. This is considered to be a milestone in the theory of spectral graphs. And you put the conjecture that almost all graphs are post-structural. Conjecture that almost all graphs are post-structural. This remains unsolved even today. Because you don't have a tool to address this problem. So here the main thing is this: constructing two trees which are post-structurally rooted. So one of them can be replaced by other without affecting the spectrum. So that is the thing. So this touch was done through computers. Ultimately, he found it, he puts answer. How we are able to get this, we don't know.
Sir, is age is a tree? Age? Is it a tree?
He wants to the two rooted trees. Okay, there is a root for the first tree. 9 vertices. I put 9 vertices roughly. Such a tree. This is one limb. Similarly, if you put another limb with a root, it may be different. Right. Another limb. He searched through computers and found two rooted trees such that they are prospectal. After removing the root, it remains prospectal.
What about age? Age is
What about
age.
Is H a tree? That is a question.
here?
Is it a tree?
Upper age.
Right,
H graph,
right,
it's a tree.
right. Right, because almost all trees are post-structural. All graphs under the contention are trees. So now he takes an arbitrary large tree. He proves that one of these two limbs is sitting there.
If we take age, another graph.
Another tree.
Not if I take graph, then you
Okay.
will not prove like.
So you want to prove almost all graphs are post-structural.
Yes.
Okay.
They then
You see, but the problem is, we don't know the existence of two objects which are prospectively rooted, and one of them is sitting in graph of R. Okay, one of them must sit inside the graph of large R as a sub. That was able to prove what is. Giving a tree of large order, he proves either T1 or T2 will be sitting there. So if T1 is sitting there, he remove it, put T2 there. So that gives a first vector tree of the original one. So that is the idea of the proof. So such a tool is not available for general graphs. First of all, you must identify a subgraph such that that graph sitting inside any large graph. That we are not able to get first. That's the main difficulty in the generalization of this set. So almost all graphs are perspective. Seems to be difficult. To avoid this problem later, one person, I think his name is okay. So the reference is not to be articulated, doesn't it? So one person developed a method for finding course vectorly rooted graphs, not necessarily trees. He found a method of constructing course vectorly rooted graphs. And perhaps this may help as a tool to prove the conjecture of Shrunk. Okay. And his method, I can briefly describe. What he did is, he took two perspective graphs. G1 and G2. Okay, perspective. Take two perspective graphs. And then choose an orthonormal basis. Let us assume that the spectrum, common spectrum is lambda 1, lambda 2, lambda 10. Both the graphs of the spectrum is bigger than co-spectral. Both of them have same spectrum. If formed an orthonormal basis for the first graph, U1, U2, UN, orthonormal basis. And for the second graph also, another orthonormal basis of eigenvectors. With the property that A G1 Ui is lambda I Ui. Thus Ui is eigenvector or lambda I. And A G2 Ui is lambda I. Bi is lambda I. It carefully chose orthonormal basis for both the graphs such that same lambda I goes for ui and dA. Yes, they're co-spectral graphs. Okay, same spectrum. Then we got this. Then we got the unit vector 1000, the usual unit vector. And we proved that G1 and G2 are co-spectrally rooted graphs. People already completely finished. Okay, these graphs are co-spectrally rooted graphs. People only if EJ inner product E1 inner product SI equal to E1 E1. For all. If these figures are equal, then we prove that the two graphs are co-spectrally rooted. So this simplified the full function because this method easily gave two limbs which shelf for searching part. Shelf for searching part you wouldn't give. This theorem gave a simpler method of getting those pieces. So Schwenk proof was better understood with this theorem. Better understood with this theorem. Okay. So almost all trees are co-spectral and almost all graphs are co-spectral. It's a conjecture. You can try to prove a similar thing. You can prove almost all unicyclic graphs are co-spectral. So don't go to all graphs. The unicyclic graph is comfortable and it's close to the tree. Is that right? Such a graph is called a unicyclic graph. Because exactly one cycle. A graph having exactly one cycle is unicyclic graph. What advantage? If you remove 1 year from the cycle, it becomes a tree. Okay? Once you remove 1 year from the cycle, it becomes a tree. Then almost all trees are co-spectral. Try to now manipulate and prove almost all unicyclic graphs are co-spectral. This may be possible. This may be possible to start with. So I propose a conjecture that almost all unicyclic graphs are co-spectral. Is in between the two. He said almost all trees are co-spectral is true. Almost all graphs are co-spectral is conjecture. I put an intermediate conjecture to travel. Almost all unicyclic graphs are co-spectral. Once we prove this, I have to prove almost all bicyclic graphs are co-spectral. What's a bicyclic graph? What's the bicyclic graph?
Two cycles.
Huh?
Two cycles.
No, that is not the definition. Slightly different. The unicyclic graph comes when you starting from a tree and add one edge. That gives you unicyclic graph. Now start from a tree, add two edges. That is called bicyclic. Two cycles will be created, sometimes more than two will be. Okay. So I'll take a tree, add two edges. I'll take a tree. This is a tree. I want to add two edges. I add one edge like this, one edge like this. Now you have three cycles, two triangles, one paper. The number of cycles is three, but still I call it bicyclic graph. Bicyclic only means add two edges to a tree. That's all. So this is my first skill exercise. Second practice. Just I want you to don't jump to all graph. Slowly keep moving. So if you prove this, I think it is provable. Possibly it can be tried. And there's a good chance of the success. If there is no success here, definitely the wicket is retirement. Because we see all graphs are posted. Almost all graphs are posted. If we get stuck even in unisecond case, then the possibility that original conjecture is almost zero. That's how I interpret. So I have more step by step. Good. Now, let us go to a list of problems for further investigation. Okay, that's very crucial. And tell you why I have chosen this problem. These problems for research. The research problems, not exercise problems. First of all, there are several types of spectrum. I will concentrate on our usual spectrum, adjacency spectrum, then Laplacian spectrum, then signless Laplacian spectrum, and then distance spectrum. These are all four types of spectrums which have been widely investigated in literature. Okay, Laplacian spectrum, signless Laplacian spectrum, and distance spectrum. So here the matrix is adjacency matrix. Here it is a diagonal matrix, degree diagonal matrix minus the adjacency matrix. This is the matrix under consideration. Here the degree matrix plus the adjacency matrix. Here the matrix is called D, where Dij is the distance between VA and B. All these are symmetric matrices. So you have given four different types of symmetric graphs associated with any graph. With respect to each of these, we can study spectrum. The first three has been investigated substantially. For four, not much progress has been made. But still there's a scope. Because the experts are believing that this spectrum captures the graph more easily. Captures the graph. Because here for the ordinary spectrum, you have a cospectral graph of order 5, 6, 7, 8, 9, 10, 15, 16, and so on. Here, in the distance case, the smallest order of a distance cospectral square is 16. As on today, the smallest order of distance cospectral graph is 60. That means up to 15 vertices, no cospectral graph. So that means the graph is completely captured the spectrum at least up to 50 vertices. So therefore, people are believing that this spectrum captures the properties of graph in a more efficient way. And therefore, it is worth studying. That is what experts have put as comment. But not much has been done. So, first problem is different four spectral theories. More are there. Only the first thing has been extensively studied. Laplacian also has been substantially studied. And signless Laplacian to some extent. And this is very little extent. So you have four different types of matrices. All of them are symmetric matrices associated with the graph. So I can define the spectrum with respect to any of these four parameters. First major okay. If for example, we take a graph like this, matrix is very different. Distance matrix. It captures so many things. The graph is like this. Your first term of the matrix will be 0, V1 to V2, distance is 1, V1 to V3, distance is 2, V1 to V4, V1 to V3, distance is 1, V1 to V4, distance is 2, V1 to V5, distance is 3, V1 to V6, distance is 3. If the matrix becomes very, very different. I said that will come here as symmetry. Let's start V2. V2 to V3, it is 1. V2 to V4, it is 2. And here 3. So I can choose this side. Like this, you can complete. Compute the distance between the vertices and put it as eigenvalue. Then the matrix becomes completely different now. It's not a binary matrix, but still a symmetric matrix. Because of the distance sitting inside the matrix, graph property is easily captured. The graph is easily captured. That is why people say that this spectrum is worth investigating. Okay. So whatever we have developed in our course, you can try for distance matrix. You get good results. Good. Now, my first question is when 0 is in the spectrum. This problem too. Equivalently, when G is singular or non-singular. Non-singular means spectrum 0 will not be there. Equivalently for what? And when eta G equal to 1. This is more specific. Characteristic graphs. Eta G equal to 0 and eta is equal to 1. We have constructed infinite families of graphs with eta 0 and infinite families of graphs with eta 1. But we don't have any general theorem. This, if you do any work on this, even if you don't characterize, if G is like this, then eta is 0. Or if eta is 0, then something happens. Even such a thing is enough. It is accepted as a paper. Because, as I told you, eta G equals to 0 means that for a chemical law, the corresponding molecule is stable. So they want to understand which molecules are stable. That depends on whether eta is 0 or not. So if you do any work on this graph, on these problems, 2, 3, 4, it will definitely get accepted in the books. Especially the chemical applications of graph theory will immediately accept it without any problem. So one observation is if the graph has 2 vertices U and V, such that they have the same open neighborhood, they are not adjacent. They have the same open neighborhood. Then what happens? 2 vertices have the same open neighborhood. What's the meaning of this? In terms of adjacency matrix. Both of them have the same set of neighbors. Identical. The 2 rows are identical. That means 0 comes in the spectrum. It's such simple observations. These such vertices are called twin vertices. They are twins. They have exactly the same neighbors. They have exactly the same set of neighbors. So if a graph has a twin vertex, like this here, these 2 vertices are twins. Yes, both of them have the same neighborhood, namely the middle. You can immediately conclude for this graph nullity is more than 0. Right? So, like this, you have to think of interesting properties of a graph which forces that 0 comes as an eigenvalue. That's the thing. I gave this very simple example, but the converse will not be true. I can give so many graphs where the nullity is 0, but still you don't have twins sitting there. Okay. These 3 problems, any partial solution itself will give a good paper. Another area which is completely unexplored is about the eigenvector centrality. Let us recall the definition again. Take any graph G, take the largest eigenvalue, that's the spectral radius, take the largest eigenvalue, it has multiplicity 1. So take the eigenvector corresponding to this eigenvalue, and current probability theorem says that there is an eigenvector such that all the x's are positive. You make it a unit vector, then xi is called the eigenvector centrality of the vertex J. Okay? So it's not easy to compute. You need a computer. You have to compute this. When the graph is large, catch the largest eigenvector and catch the eigenvector corresponding to that eigenvalue and make it a unit vector, and then the ith coordinate of that eigenvector is the eigenvector centrality of the vertex Vn. Okay, so now my problem 5 is for which vertex this object is maximum or minimum. See, degree, maximum degree means it has lot of contacts. So what is the meaning of saying eigenvector centrality is maximum? Where it happens? Okay, where the eigenvector is maximum, where it is minimum. So you develop some properties of this type. It is extremely significant for biological application. Because in biological network, they are ranking the vertices using this number. So first they put the vertex with the highest eigenvector. Next one. So these numbers are used for ranking the vertices of the network. And vertices with high rank are significant for that particular biological process. That is how they are applying this. But no change has been developed as of today. Nothing is known about for which vertex this is maximum, for which vertex this is minimum. Any result of this type is very significant from the application perspective, and we will easily accepted for a good journal. So this is my first problem. Here after two sets. But the definition is clear. Eigenvector centrality is clear.
The question is why is it very unique?
Why?
Why we are making it a unit vector?
Because there are so many eigenvectors for a given eigenvalue. It's order dimensional subspace. I want to fix it uniquely. So how to fix it uniquely? Normalize it. That's all. Otherwise, it will multiply. That's all. And then dividing by now, nothing else. It's not going to affect the maximum or minimum ratio. Okay. Fine. Fine. So this is here two problems sitting inside. Maximum is one problem, minimum is another problem. Where it contains the maximum, where it contains the minimum. Oh, nothing is not worse. Nothing is not. But we need it. We need it. That's all. So myself, the problem is, which I already mentioned in the lecture. Problem 7, nullity versus how they are related. Chemistry perspective is, if nullity goes up, energy comes down. Already one student said that he has got some idea that this is not true. That means he is moving towards solving this problem. Okay. One student is moving towards solving this problem. As nullity goes up, energy comes down. He says he has got some idea of an example of a graph the nullity goes up and energy also goes up. If that example is completely developed, it can become a good paper. Okay. So nullity versus energy. It's a very good topic, which is significant from quantum chemistry perspective. Then diameter versus this, which is discussed it. If m is the number of discrete eigenvalues of a graph, then m is greater than or equal to or less than or equal to diameter plus 1, that is greatest. Is greater or less than or equal to, right? Check. There's upper bound and lower bound. For computer graph, m is 2, d is 1. Okay. So m is greater than or equal to the diameter, less than or diameter.
What's the number?
The number is greater than or equal to less than. They are unlimited.
This is correct. Greater than
Greater than or equal.
because I, A, etc., A power B will all be different. Usually polynomial will have at least
Right. Power is fast. It's greater than or equal. Sure. Okay. Now we see question. For which graphs m is equal to diameter first. This is my 8th problem. I will show many examples of graphs for equality. Computer graph is there, complete bipartite graph. Has 3 distinct eigenvalues, plus or minus root of r and 0. And diameter is 2. So computer graphs, complete bipartite graphs, are examples of graphs where equality is 2. Okay, so there are so many graphs, but I want an equal body here. It's a very good problem to work. Problem. So much of work is being done. Which graphs are completely determined by spectra? That means such a graph does not have a post-spectral rate. Such a graph does not have a post-spectral rate. That means that graph is completely determined by this. For example, we can take line graphs or caudal graphs, interval graphs. Take a family of graphs and try to find whether that family is uniquely determined by the spectrum. It's a very significant problem. The simplest I can give you is the Peterson graph. It is uniquely determined by the spectrum. The Peterson graph, it has 10 vertices, 3 regular, 15 edges. And the spectrum is 3, 1 to 21, and then help me to write the numbers. Yes, it's there with you. I can step up to my book.
1, 4,
The numbers are completely determined by this. The previous pixel.
Minus 0.5, then 4 5. Okay, 2 4. 1 5 minus 2 4. 1 5.
2 4, right?
1 minus 2 5 4. 1 and minus 2
Minus 2, okay.
with multiplicities 5 and 3
So minus 2
with 4.
with multiplicity 4
1 with 5.
and
1
1 with multiplicity
5.
5. Okay. I correct that Peterson graph is only graph. Okay. Peterson graph is the only graph with this vector. That means that graph is uniquely determined by the spectrum. Why? Because there are only 3 distinct eigenvalues. So the graph is strongly regular. Okay, the graph is strongly regular. It is 3 regular. Why it is 3 regular? So I am taking, let G be any graph. I don't say it's Peterson graph. Let G be any graph with spectrum this much. What can I say about the graph? I agree with the graph. I agree with that. A graph has this spectrum. Nothing else is not real. Okay, a graph has this spectrum. Therefore, number of vertices is that immediately. There are 10 eigenvalues. So number of vertices is that. Then what is the number of edges? You know the formula? You have to put sigma lambda is square and 1 by 2. That's a square. That's a square and it's a degree.
Raise a base square and
So we just find out. Sigma lambda is square. So it is 3 square is 9. Then 2 square comes 4 times. 2 square comes 4 times. And 1 square comes 5 times. So this is 30. So half times that is 20. So number of edges is 20. We are moving towards Peterson graph. Vertices 10, edges 20. Is it 3 regular? Now can you conclude it is 3 regular? 10 vertices, total number of edges should be 15. 10 vertices, total number of edges is 15. What is the degree of any vertex? Assume it is k. So 10 times k is 30, twice the number of edges. So 10 times k is 30. Therefore k equal to 3. That is 3 regular.
we didn't do that.
Just this, you see the spectrum, what's the appearance?
With that we are using that.
There is no triangle. The triangle will be coefficient of x power 7. And you can prove that that's the lesson. It has a 5 cycle. Rather direct ratio. The ultimate is Peterson graph. Simple form. I can prove that this graph is nothing but line graph of paper. And that is the reason. So any graph with this spectrum is a Peterson graph. The Peterson graph always begins with. So now my question is, which graphs are uniquely determined by spectrum? If you find a family of graphs which is uniquely determined by spectrum, that's a paper. It's a good paper. Lot of papers are already there. Like this. Okay. So this is question number 9. which graphs are completely determined by the spectrum. Okay. Try to get more spectral properties of light. As it is, we know that whenever lambda is an eigenvalue, minus lambda is an eigenvalue. The pairing theorem. That's already information that is known. Can get some more information about spectrum of bipartite graphs. You could expect that it is possible. The survey article poses this as the very important topic. Try to develop, get more properties of spectrum of a bipartite graph. Okay. That is my 10th question. More particularly, what can you say about spectral properties of trees? The particular case. This may be perhaps more easy. Yes, every bipartite graph, every piece of bipartite graph is a smaller class. So first try for a smaller class, then go for a larger class. So I do not come across any theorem on how a spectrum of a tree looks like. The spectral properties of trees is completely open. Another difficult problem is study integral graphs. Integral graph is a graph in which every eigenvalue is an integer. No fraction comes. A graph is called an integral graph if every eigenvalue is an integer. For example, C4. The eigenvalues are 2, -2, 0, 0. Such graphs are very limited in number. We don't have big numbers. So try to construct or study properties of integral graphs. It's again considered to be a difficult problem. Then this thing is very tough. Spectrum of direct graphs. Some work just been done. Some work just been done. Not much. But basically the major problem is the adjacency matrix will not be symmetric. That's a first hit. Because if Vi, Vj is an arc, the reverse arc may not be present. So see, Aij will be 1, Aji will be 0. So this adjacency matrix of a direct graph is non-symmetric. So complex groups will come and makes life more complicated. But still, people have done some work, but not much has been done. There are some particular types of direct graphs which you can try. That again give you a sub problem for protein. Spectrum of tournaments. What is a tournament? Suppose a tournament is taking place, like cricket match, cricket matches, or any football game, take a tournament. Suppose there are young teams. Every group will play with each other. and there is no draw. Result will be that either A loses or wins. So tournament N teams participating. Okay. Every two teams play with each other. Every two teams play with each other. And no draw. No draw. The result is there for every match. Then I take the teams as vertices, and if A wins the game, you put arrow like this. A and B play, A wins the game, you write it. So the out degree is the score of A. In how many times he has won. The out degree is how many times the team has won. So this is a complete graph where every edge is given a direction. Yes, every team is playing. Every two team is playing. Either one wins or other wins. So you get the arc. So this is a tournament. This graph is called tournament because of the fact that it comes from tournament. It comes from a tournament. The tournament is a orientation of a complete graph. Okay. Tournament is an orientation of the complete graph. Take a complete graph, put arrow for every edge. So study the spectrum of both tournaments. This may be a good problem. Because the graph is complete, but the arrow just made it difficult. This is posed as a major property of mathematics on spectrum of direct graphs. Study the spectral properties of a tournament. So this is problem number 14. Fine. Then one area which I am interested is, I don't know how many of you know this concept. Very time. Okay. Sine the graph. Anyone know the definition of sine the graph? Sine the graph. A graph in which an edge is either positive or negative. For every edge, put a positive sign or a negative sign. Such a graph is called a sine graph. It occurs naturally in psychology because two people may like each other or do not like each other. If they like each other, put a positive. If they don't like each other, put negative. Okay. So that's a sine graph. So the example of the sine graph is this. Something like this. Put a sign on every edge. That's all. Put a sign on every edge. Such an object is called a sine graph. Can you define the adjacency matrix of the sine graph? Yes. You take BIBJ, no edge means 0. Positive edge means 1. Negative edge means -1. That's all. So for this graph, for this sine graph, what is the adjacency matrix? So my 15th problem is spectrum of sine graph. Absolutely nothing is known. The matrix for this sine graph is diagonally 0, no problem. Then V1 is adjacent to V2 with a plus sign. It's not adjacent to V3, It assumes B4 with a minus sign. So it's symmetric. I can put it here. V1, V2 is not. V2, V3 is negative. V2, V4 is 0. So I can put it here. Then V1, V4 is negative. V1, V4 is negative. It's negative here. And V3, V4 is positive. So it's a symmetric graph, symmetric matrix. The advantage is that the symmetric matrix, so you can deal with the matrix. Okay. So I can define the adjacency matrix of a side graph. This has lot of applications in social science and political science. If you take a particular state like Rajasthan or something, take all the leaders of the Congress party and put a side graph. Because you know which people don't like each other and which people are collaborating with each other. So it's a side graph comes naturally. And there's a website maintained by Thomas Zaslavsky. He's a very good friend of mine. He maintains a website where all the published results are side graph you can see. You need not travel to so many places. So just write this name and put dynamic survey on sine graphs. So in one place, you can get everything that is defined sine graph. That's a big advantage. Literature survey is very easy. One person is maintaining this, is updating it every month. Whenever he gets a new result, he puts it there. So now it's called dynamic survey. It's updated periodically. In one place, you two, three, four. One is the situation where all the three people are good friends, they know each other, they agree with each other, they can work together. So if you allot the job to such a set of three people, they will complete the work and give themselves. What about this? They don't talk to each other, they don't like each other. How can they sit together and work? So this team is absolutely useless. the work will not get completed. Now question, among 3 and 4, which team you think will complete the job and get the work done? What you recommend? You can go by voting. Which of the 3 and 4, which team will be able to complete the work and give the output? What is your choice? 3 better or 4 better? This is better.
4.
4. There's one positive, 2 negative. So there's one more part. Huh? 4 is the choice. By everyone? By anyone? Let's say 3 is better. Number 3. Which is the better choice? Is the question. This is how the subject started. Okay, this is how the subject started by one psychologist by name Heider. He started the subject purely from psychological perspective. He is a German professor, and during the World War II, 2 of his students traveled from Germany and went to USA, where his professor is working, thinking that his professor will take care. So both of them landed in his house. The 2 students landed in the house of Heider. Initially, everything was fine. All of them were very comfortable and they are having a happy life. Now, a vacancy came in the department where Heider was working. Both the students applied for the post. Now, the triangle became like this. The 2 students are competing with each other for the same job. But the professor is equal to both the students. He is happy with both the students. So the situation came like this. And Professor Ryder writes, my house is something like not a publicity inside my house. Because he's always under tension. If one student goes to the professor, starts talking, another student becomes suspicious. Okay, he's trying to spoil my chance of getting the job. So Ryder says, this is unbalance. That is how the theory came in. Okay, so this is the not a good group. In this group, A will be always under tension. Is that correct? A will be always under tension. It's something like in a family, there's one brother and 2 sisters. The brother loves both the sisters equally, but the 2 sisters are always smaller than him. What will happen to the brother? He always under tension, right? That's the situation. So essentially, I put it in a nutshell. Here's a situation where 2 enemies have a common thread. Here's a situation where 2 friends have a common enemy. Look at it from this perspective. Is it better? 2 friends having a common enemy, or 2 enemies having a common enemy? Because here, you can sit and neglect this fellow. These people can sit together, complete the job, go away. So this is called balance inside the graph. So now I want to catch through spectrum when the sign graph is balanced. Can spectrum will come to help to say when the sign graph is balanced. The definition is the sign graph is balanced if every cycle has even number of negative edges. If the even number of negative edges, somehow the balance comes in. Here is even number of negative. So this is balance. This is odd number, not balance. This is also odd number of negative edges, not balance. So can you catch balance through spectral graph theory of sign graphs? That this way I'm saying that study of spectral area of sine graphs is extremely interesting from application perspective. Okay, there can be good PhD thesis. It's not simple because the advantage is suppose you get an information about we shall say m plus number of positive vectors, m minus number of negative vectors. Suppose you get a result which involves m minus, you get a result. Then put m minus equal to 0, your original spectral theory becomes a parallel. Because if m minus is 0, no negative edge. That means ordinary graph. So, spectrum of ordinary graph can be reduced as a corollary to the spectrum of sine graph, at least in some special cases. That is why I find that study of spectrum of sine graphs is a very, very rich topic. Okay. Now, all these problems you can try for all the 4 type of spectrums. So, you have 16 problems and 16 into 4. Study this for ordinary graph, ordinary spectrum, study this for Laplacian spectrum, assign the spectrum or distance spectrum. All this can be done for any of the type of spectrums. So this is a very, very set of problems. Some of them are actually one full PhD thesis. One full PhD thesis can come from direct or tournament like that from this sine graph. So this is any questions. This will come now. We are almost towards the time. So I want to work on sine graphs. Someone can join with me again. So a group can join. We can work together on spectrum of sine graphs. Because it's a symmetric matrix. Eigenvalues are real. So everything comes. Only it's not a binary matrix, it's a primary matrix. Three different types of matrices. 1, -1, 0. Three different types of matrices. That's all. Nothing extraordinary. So it may work. Thank you very much for learning, for your attention and thank you.
Give the mic. Mic. We have started with sine graphs for my. I'll ask.
It can be the start of scope.
Yeah, which day will be?